Hi, this is Sam Urison from iQuest LLC, and in this video we're going to talk about relational and NoSQL data management strategies. As you may have noticed, especially in the last few years, storing and managing data through relational databases is no longer the de facto standard. There was a time when we wanted to design a new application or there was a need for managing some organizational data. The answer was always go to a relational database, but that's just not the case anymore. A lot of the emerging technologies in data management have become quite mainstream in the last, I would say, 3, 4, 5 years. And the first concept that we should kind of touch on is polyglot persistence. So if we kind of look at the diagram on the screen, we notice that there's an application with 3 databases. It appears there are 3 databases in the back. And if you notice them, actually, they're not just 3 databases, but 3 different types of databases. There is a relational database, SQL database, there is a document database, and there's a key value database. And if we go back to the definition, what we notice is that we use different types of databases for our applications, and then we choose these databases based on what they do best, kind of a use case scenario. And then we spread our data across multiple database types. You may or may not have noticed it, but basically this is becoming very, very mainstream. A lot of applications that are in demand, especially applications that are on the internet, are using this approach. And in this presentation, we're going to get into the reasons why this approach makes a lot of sense. With that said, let's kind of look at our database types. Now, on the left, you'll notice that there's the good old relational database, and some examples of relational databases are Microsoft SQL Server or MySQL or Oracle or IBM DB2. By the way, these lists are not complete and they're not in any particular order. I just wanted to come up with some examples. That's all there is to it. If your favorite database is not in the list, don't be alarmed. It might be a great database. It's just that when I came up with these lists, it may not have occurred to me. Now on the right, if you notice, all of these 4 different types of databases, document, key value, white column, and graph, are all under NoSQL databases umbrella. So that's because NoSQL is an umbrella term. It's kind of an unfortunate term in my opinion, because SQL or SQL stands for Structured Query Language, and some of these databases actually use an SQL-like language to run queries. So what they really meant by it was that it's a no relational or non-relational database. That's what they wanted to say, but this phrase became popular and it's widely accepted. So when we say NoSQL database, it doesn't really indicate a particular type of database. It just means it's not a relational database. And by the way, there are other types of databases, but I just wanted to focus on the ones that are very common. If we're going to create a new application, especially something for the web or mobile, chances are we're going to tap into one or more of these database types: document, key value, white column, and graph. And I mentioned some examples under each category. Now let's look at each and every one of these briefly. I don't think relational databases need much introduction. They've been around for a long time, and most of us have used them. But just to kind of include relational databases in our presentation, let's kind of touch on it real quick. The approach in relational databases is to take the data and break it down. And then what we do is we store our data in tables that contain uniform data. What we mean by that is that we have 2 tables on the screen. The one on the left is let's say a student table, and if you notice that this table only contains information about the student: first name, last name, and gender, along with the ID number. You're not going to find any other information in that table, course or registration. The table on the right is maybe the registration table. It indicates the courses that each student has registered for. And one thing you'll notice right away is that the table on the right doesn't contain any information about the student except the student's ID. And this is the main concept. It's called normalization. The idea is not to duplicate our data. And so what's the advantage of it? For example, if our second student, Jane Doe, who's female, gets married and changes her last name to, let's say, Green, we don't have to go and update hundreds or thousands of records. We can just go update one record in the students table. And anytime we reference that particular student, her new and updated last name will appear automatically. So managing data in relational databases is much easier due to the normalization practice that we use. And whenever we need to create reports or certain applications that need to show data from different, different domains of a business, that's when we create relationships and join these tables together to be able to paint a big picture. You'll notice that on the left it says set schema. What that means is that the table's structure, the ID, first, last name, and gender columns are predetermined by the person who designed these tables. And that doesn't mean they can never be changed. They can be changed. But if we have a production database with lots and lots of records in it, it really is not a lot of fun to modify these tables, though obviously we do it all the time because nothing in life is static. Everything is changing. So as the business needs change, we go back and change our database structures. One last thing that I should quickly mention is that as you see above the ID column on the left, it says PK, that stands for primary key, and the student ID column is the FK, that stands for foreign key. So that's basically how we create relationships among these tables. So that's the one column that we reference. So student ID 123 is a reference to John Smith. Student ID 234 is a reference to Jane Doe. And as I said, this is probably a very familiar concept to you already. The next database type that we're going to examine is a document database. And just by looking at it, you can see that it looks much more complex and rich. And in the case of relational databases, we were storing our data in tables. In document databases, there's no such thing. They're typically called collections. And then we were storing our records in rows, with each column kind of breaking that data down into simpler units, if you will. And in the case of document databases, we don't do any of that. And instead, we have these rich JSON objects that are called documents. And the other thing that you may notice right away just by looking at these examples is that they don't contain uniform data either. Looks like each JSON object or each document is a student document, and even though they contain student information, they also contain course information. And it's not that difficult to see how this can actually have performance benefits. If we were to use a relational database, we would obviously have to break this down into multiple tables and store different types of data in different tables, and then whenever we needed to generate a report, we need to bring that data back together. And that has some performance and cost implications in terms of, when I say cost, I really mean execution cost in terms of system resources, whether it's CPU or memory, or the time it takes to perform those queries. And if we're using a document database, we can just pull this single JSON object. It's basically text-based, so it's tiny, maybe less than a kilobyte in some cases. Just by pulling that one single document, we have all the data that we need. So we didn't even get into too many of the benefits of this, but I think that one is pretty obvious. And the second thing that I'd like to point out in this screen is that if you notice the student document on the left, John Smith's document on the left, has the date of birth property. His date of birth is March 8th, 1999. And we don't see the date of birth property at all for Jane Doe. And this is what we mean by flexible schema. Basically, we can have data with different structures to them. It doesn't have to be just students either, by the way. We can have a single database with a single collection in it, a single document database, I should say, that stores student information, course information, e-commerce purchases, and anything else that you can think of. So in the case of relational databases, we always create separate tables to be able to kind of keep and store these different types of data separately. In the case of document databases, there's no need for it. We can simply store everything in one place. And in our design, obviously, we have to come up with something that's going to tell us how they're different. For example, we may have a property called type and call it student to identify student documents, and maybe call it purchase for e-commerce website purchases. But this kind of gives you a generic idea. And by the way, if we decide to add a date of birth property to Jane Doe's document in the future, we can do so very easily. So adding a new property doesn't mean we have to go through all the existing documents in our database and update all of them. It doesn't mean that at all. Each document can have a different structure to it, and the database is perfectly happy with that. Our next database type is a key value database. One of the kind of more popular examples of this is the Redis database. It's used for caching purposes quite often because it's an in-memory database. But it's kind of helpful to use that example to visualize what a key value database looks like. One thing that you may notice right away is that the schema seems to be set. There's the key and there's a value. For visualization purposes, we're kind of depicting this as a table. But the main point here is that the value seems to be very flexible. So the first two examples contain a value of string, but if you look at the third one, the favorite colors, the value for favorite colors appears to be an array with 3 entries in it: red, white, and blue. And yet the next one appears to be a JSON object. We have user ID 123, and looks like the value for it is a JSON object that includes the person's name, first name, last name, and gender. So the key here is that the schema seems to be fairly set, but both the keys and values are very flexible. Even keys are flexible because there's no rule that says they all have to be strings. We can actually use numeric values. The only requirement is that the keys must be unique. So if I decide to use WY key again, I couldn't. There's only one entry for WY that's whose value is Wyoming, and that's it. The next database example type is the white column database, and sometimes they're referred to as tables. Now, even though it looks like a table, please do not confuse it with a relational database table, because they really have nothing to do with each other. But for visualization purposes, it's quite useful to think of these types of databases as tables. And the main difference between a white column database and a key value database is that the value part doesn't have to be a single column. In the case of key value, there was the key column and then there was the value column, and that was it. In this case, we can have many, many more columns. So here we're looking at, this happens to be an Azure Table Storage example, and in this case, the key actually is in 2 separate columns, partition key and row key. Together, those 2 columns represent the key. And then the rest of them you can think of as the value. So if we look at the first entry, it's a student entry, row key is 1, 2, 3, and there are 2 additional columns, first name and last name. Now, if you compare that first entity with the last one, which is also a student entry, 2, 3, 4 for Jane Doe, you'll notice that in the case of Jane Doe, we have 1 additional column, gender, and we have the gender information. Now, you may have noticed that I kind of grayed out the columns that are not used. And I did that for a reason. The reason is that as far as the database is concerned, for that particular entry, let's say John Smith, the only columns that exist for John Smith are partition key, row key, first name, and last name. The gender, name, and description columns do not even exist. Now, if you're coming from a relational database background, you may think that, for example, the gender column exists for John Smith and its value is null, but that is not the case at all. As far as that particular entry is concerned, gender column doesn't even exist. So this is an example of a flexible schema. And by the way, that doesn't mean we're set with that. We can go back and add the gender column for John Smith and add the value in there. And we have that flexibility to do so. Secondly, you'll notice that the second entry is a course and looks like it has the partition key and row key, and then it skips first name, last name, and gender. Instead, it has name and description. So, as mentioned earlier, for this particular entry, there is no first name, last name, or gender columns at all. If we were to pull this particular entry from the database, we would notice that the only columns we have are partition key, row key, name, and description. And this is a great example of mixing different types of data in a single table. And there's one other thing that I'd like to kind of point out here, and that is point number 3. It says not all columns may be indexed, and we use composite keys. So this is an important point. This is not the case with all wide column databases, but some wide column databases will say, look, I'm not gonna index all the columns. What I will do is I will index the key columns. Again, we're looking at the Azure Table Storage example here on the screen, and in this case, Azure Table Storage will only index partition keys and row keys, nothing else. So if I wanted to run a search, run a query, and say the last name must be Smith, I really couldn't do that efficiently. I can run it, and it will cause a table scan. So if I have 1 million records in my Azure Table Storage table, that means my query will have to look at each and every entry one by one. So it's going to take a long time. It's not an efficient way to run a query because the database does not index those columns. It only indexes partition key and row key columns. Again, this is specific to Azure Table Storage and some other wide column databases. So whatever you're choosing, you need to kind of look into that. On the other hand, some wide column databases will actually index all the columns. For example, recently Microsoft added the table API to Azure Cosmos DB, which is very similar to this, but that particular database will index every single column. And so the question is, what do we do in those cases? If these columns are not being indexed, how do we find the information that we're looking for quickly and efficiently? So the second example the second entry is a good example. It says SCI for science, and there's a dash, and then it says Math 101. So this is a good example of a composite key. We decided that we're going to include some kind of prefix in our row keys to indicate that this particular class is a science class. So what we could do, let's say if I'm running a query to get a list of all my science classes, what I would do is I would say the partition key is going to be course, and the row key starts with the letters SCI. And this is a very effective way to quickly get very efficient results for our queries. Because the row key is actually indexed, we have the ability to specify partial values. It doesn't have to be that row key equals sci-math 101. We can say the row key starts with whatever. So this is completely up to us. This is where the design and engineering come into play. We need to design this carefully, and one of the main benefits of doing this is that you'd be surprised. It actually impacts your application. It actually ends up producing pretty good architecture. But like I said, this is not always the case. Some wide column databases will index the other columns as well. And we mentioned that one example of a white column database is Azure Table Storage. And we're going to kind of get into why these tables, these different types of databases are useful and the scenarios for which they're useful. And the next example is a graph database. And graph databases are all about relationships. I would say that maybe this is the one type of database that has more specific use case scenario. I think document databases, relational databases, white column databases, they can be used for almost any purpose. You can store transactional data in them. You can store student information, courses, e-commerce website, purchase transactions, so on and so forth. They're used for so many different purposes. But when it comes to graph databases, we seem to focus more on relationships. And graph databases are all about nodes, edges, and properties. So what you're seeing on the screen are the nodes. These are John Smith is a node, Jane Doe is a node, Math 200 is a node. And then we create relationships among these nodes, and we call them edges. So for example, if you kind of follow the line connecting John Smith to Jane Doe, and there's something on it that says friends with, it's kind of defining what that relationship means. Another important point is that not all relationships are two-way. We can define one-way relationships. For example, if John Smith is friends with Jane Doe, chances are Jane Doe is friends with John Smith. But if you follow the line connecting John Smith to Biology 101, we can say John Smith studies Biology 101, but not vice versa. And these types of databases are very common for social networks because they really help us very efficiently define and query relationships. For example, we could say, we can run a query against this database and say, we'd like to get a list of all Jane Doe's friends who have pets. And our query would return John Smith because John Smith has a relationship with a cat, has a pet. That's probably a better way to put it. But this is a very specific use case for graph databases, and they're really highly optimized to handle that type of data. And as a result, as I said, they're widely used in social networking applications. Now, this may come as a surprise a little bit if you're coming from a relational database background, because typically a database type was a database type. A relational database was a relational database. But now we're kind of, as part of this NoSQL revolution, if you will, now we end up with databases that can handle multiple data models. I put two examples on the screen, the Azure Cosmos DB and Amazon DynamoDB. In the case of Cosmos DB, it handles documents, tables, and graph. One important point that I'd like to make, though, is that different models may not be in the same database. What I mean by that is that let's say I created a database, a Cosmos DB database, document database for customers, and I called it customers. And I have documents in it. We looked at it earlier. They're basically JSON objects. And I could not, in the same exact database, put some graph data. I can create another database, another Cosmos DB database. But as I create that database, I will specify that this database will support graph data. So having said that, this is my hunch. This is not a fact. I'm speculating here, but I have this hunch that in the near future, we're going to have multi-model databases that will support different models in the same database. Because there seems to be some demand for it. I'm actually one of them myself. I would like to have a database, say my customer database, which is a Cosmos DB database, and I would love to have documents in it, as well as graph data, as well as maybe some table data. And I, like I said, I do feel that in the near future we will have multi-model databases that will support multiple models in the same database. Now, this is maybe an interesting dimension. As we look at databases, we should also look at cloud databases versus on-premises databases. And in this context, I want to clarify that when I say cloud database, I'm talking about database as a service, because it is perfectly possible and fine to run on-premises databases in the cloud. For example, if you're running a MySQL database on a server on-premises at your office, you could run the same exact database in the cloud in a virtual machine. So when I say on-premises databases, I'm really referring to databases that require an instance of a server. Whether that server is virtual or physical, it doesn't matter, they require a server. A cloud database, on the other hand, or database as a service, is something that runs as a service. It doesn't require for us to set up a server virtually or physically. So with that said, here are some of the key characteristics. A cloud database basically is a managed database. All the underlying layers, network, security, operating system, or the database application itself, are not managed by us. They're managed by the provider, whether it's Microsoft or Amazon or Google, they manage them. And even database performance, they manage these things for us. And cloud databases are not limited to just relational or NoSQL. Both are available. For example, if you look at the examples, Microsoft offers a cloud version of its very popular on-premises SQL Server database. They call it Azure SQL Database. So that happens to be a cloud database that is relational. But Azure Cosmos DB, as we looked at it earlier, supports different models, documents or graph data or tables. And when you look at on-premises databases, they're not managed. The simple way to put it is that it's your baby, you take care of it. So if there's an update to the database software, say SQL Server, let's say Microsoft released a new version of SQL Server or some kind of update to SQL Server, we have to install it ourselves. We have to set up servers. We have to set up or update and maintain the operating system. All of these things become our responsibility. And some examples of on-premises databases include SQL Server, Oracle, MySQL, and many more. Now, this is a really important point. Whenever we introduce NoSQL databases into our mix, into our data management strategy, we have to maintain data integrity ourselves. It becomes our responsibility. So I just wanted to demonstrate this with this example. Let's say I have my students in a document database. So I have the document on the left, and I called it master. That's where that's where the data is coming from. If I need to know anything about the student, this is the master record that I go to, John Smith. And then on the right, let's say I have this white column database. It looks like an Azure table, in this case, Azure storage table. And so we have the test information, test data. So we see the student, and then we know that the student took a certain test and, scored a certain grade. And if you notice that we have the name John Smith or Jane Doe with each entry. And going back to the previous example, if Jane Doe were to get married and change her last name to Green, we would have to go update these records in the table storage so that it's going to read, for example, the second record, the second entry is TSQL 101, is the partition key, row key is 234, which is a reference to Jane Doe. We would have to update that and say the name is Jane Green. So why do we have the name in the first place? It's really for convenience and performance. I mean, we don't want to have some data coming from, let's say, our white column database, and then let's pull some more data from the document database and then somehow merge them together. This would have a terrible performance. So what we're trying to do is, again, if you're coming from a relational database background, you may struggle with this a little bit because I did. You want the data to be consistent, kind of like automatically on its own, because in the old days, the relational database, right, took care of that for us. But that's not the case anymore. So we're saying, okay, John Smith, or the document database is the master record for the student. So anytime there's a change pertaining to the student, I'm going to make that change in that table, in that database. But if I have corresponding records in other databases, it will be up to me to make those changes. And this is something very important. And we tap into our applications to handle those things for us. And I can pretty much guarantee you that even though this may seem a bit cumbersome, it has tremendous scalability and performance benefits, because it's so much easier for an application to scale up. This maintenance of data, for example, can be handled by an application that runs as a background service. It doesn't even have to have an interface. We can set it so that it runs all the time, and anytime a change is made to a record, to a document in a document database, it may just pick it up and go find corresponding records in other databases and make the necessary changes. Or we may set it so that it runs 3 times a day, for example. It could be, like I said, a worker role that runs in the background and handle these changes. Now, scaling that up as the number of or the volume of data goes up, scaling that background process up so that it can keep up with the maintenance is very easy. But if we were to contain ourselves to a relational database and try to scale up as our data levels reach tens of millions of entries, you will notice that that is much more difficult to handle. Scaling up a relational database is much more difficult and costly compared to scaling up a scenario like the one on the screen. We simply have a document database. If it's a cloud service, there really is no limit. It can scale up all day long. And then let's say we're using Azure Table Storage to store this data, kind of a transactional data. And so now we have to take the responsibility of maintaining our data and data integrity. And like I said, in this case, we would just simply create a simple application that will perform these updates for us. And creating a second, third, fourth instance of that background process is extremely easy to do. And cost-wise, it's a lot less expensive. I don't want to call it cheaper because you're still spending money, but it's a lot less expensive to scale up a simple app running as a background application compared to scaling up a relational database. Now, you may say then, okay, this is all fine, but really, what are the reasons for even getting into polyglot persistence? There are 3 that I can think of: performance, scalability, and cost. It's much easier for NoSQL databases to scale up to really extremely high levels. A lot of the websites, popular websites such as YouTube or MSN, for example, tap into these NoSQL databases in the back end. And performance, as again, we talked about it earlier. When you look at the simple document, a simple JSON object that contains all the information that we may ever need, pulling that tiny little document is going to be always much faster than for us to go into a relational database and then create joins among multiple tables and create these complex select statements. It's going to be always provide much better performance. And performance and scalability always relate to cost. Now, with that said, I've come up with this chart, if you will, and I just want to mention that this is not something super scientific, but it is scientific enough that it is based on my personal research and observations. So I came up with 3 different. I'm comparing 3 database types: relational, document, and table, on 3 different categories: cost, performance, and scalability. What I've noticed, starting from the left, is that relational database is costlier than a table, a white column database, for example. but cheaper than a document database. And this is taking a few things into consideration: the space that data consumes when we persist the data on the hard drive, if you will, and the cost of retrieving it, and the CPU and the memory involved to be able to pull that data. When we look at the cost and the final, the bill, when we receive the bill from, let's say, the cloud provider and says, this is how much you need to pay for having these databases. For similar data, you'll notice that the document database actually costs a little bit more than a relational database, and the least expensive is the table. However, when you move to the performance, you'll notice immediately that the document has the better performance. Maybe the second, in my personal experience, is the table, and then relational. And then when you move to the right, when you look at the scalability, there's almost no comparison. Document databases and table white column databases always scale up much more easily, and scaling a relational database, like I said, is not an easy task. And so as you can see, it's not, one thing is not necessarily the dominant factor here. You need to really take these three things into account in making your final decision as you're determining your data management strategy. And another important point is at the bottom of the screen, which is at this point in time. This is something that's dynamic. It's ever changing. I can tell you one thing, that the performance gains in relational databases are quite impressive recently, especially now that they run in the cloud. So this is what I'm seeing right now. This kind of picture, this landscape may change next year or in the next 6 months. It may be possible that maybe relational databases will come down in cost and be very comparable to table storage or white column databases, for example. That's possible. But as of now, this is what I'm seeing. And your data management strategy, I think, needs to take all three factors into account: performance, scalability, and cost. And so just wanted to quickly look at one example of what I'm talking about. So let's say I have a relational database in which I store my e-commerce website transactions. And I just came up with a very simple table here. So as you can see, product 123 sold 3 times. First entry is $30, third one is $47.50, and the last one is $9. So if I wanted to create a report that tells me my total sales by product, I could simply come up with a select statement using an aggregate such as the sum function, and I could get this number very easily and very quickly. And this works perfectly fine when dealing with records that are in the thousands. Even a million or two would not be an issue. But when the numbers go up, when the volume goes up, that's where the story changes. So here's an example. This is a quick little screenshot from a YouTube video of an artist that I happen to like, Lindsey Sterling. And when I took this screenshot, the number of views on this particular video was over 95 million. And almost a million people, a little bit less than a million people, gave this video a thumbs up. And a little bit less than 10,000 people gave this video thumbs down. Now, if somebody clicked on this video on YouTube, and let's say we stored transactional data in a relational database, coming up with these numbers would be basically terrible in terms of performance. It would take a long time to compute these numbers on the fly. So I came up with my version of YouTube's solution. So what I think they do, this is my speculation, but I think that what they do is very similar. I think they're using some type of transactional database, whether it's a relational database or white column database. They're using something like that to capture each and every transaction. So in the first entry on the left, Johnny01 gave this video a vote of 1. Let's say 1 represents a thumbs up, and there's the timestamp. We know exactly when this person voted on this video. And you have 2 other users, and the last user by the name of Dark Shadow 123 gave this video a thumbs down, -1 representing a thumbs down on September 2nd, 2012. So this is where we're keeping the actual transactions, and we need to do that. We need to do that because we don't want the same user to vote more than once. We don't want, for example, Simon02, the second user, to vote again to give 2 thumbs up for this video. We don't want that. So we need to have some kind of way to make sure that we enforce our business rules. And for us to be able to do that, we must capture this transactional data. And in this case, it may prove to you that the relational database does a pretty good job because it's just capturing these transactions, and it'll scale up nicely. And as far as making sure that the same user cannot vote more than once, if we were to set the user column as the primary key, for example, the database will automatically take care of making sure that the same user cannot vote more than once for us automatically. We don't have to do anything. So that's one way to capture transactional data. But I think on the right, what YouTube might be doing is that they may be using a document database, or maybe it's some other database, but they're using another database in which they tally up these numbers. And so when somebody clicks on the link to pull up this particular video, this document on the right may be the master document. There might be another property in that document that says here's the URL pointing to the file that will stream the video. But that one document provides us with all the information that we need: the title of the video and the total number of views and total likes and total dislikes. Obviously what that means is that as things change, as more and more people view this video and more people cast their vote as thumbs up or thumbs down, we not only need to register these transactions in one database, we also need to reflect them. We need to tally them up in another database. So what are the takeaways? The takeaways are, number 1, set the data management strategy carefully. And if it makes sense, incorporate NoSQL technologies into your strategy. And the third one is very near and dear to my heart. If using NoSQL databases, we must use applications to help manage our data, and this is the crux of it, and preserve data integrity, because the database will not do it for us because we're spreading our data into multiple databases. So we need to incorporate some other technology, typically speaking, some kind of application. It doesn't have to be an application with a user interface. Like I said, it could be a back-end worker role that runs in the background with no user interface whatsoever, and its sole purpose is to make sure that our data integrity is preserved. This is pretty much it, and I hope that you find this video helpful in setting your data management strategy. Thank you for watching, and please don't forget to subscribe.